the contents of the talk aren't really necessarily completely tied to CloudStack, but using that as an example for moving automation past where we've typically done it with Puppet, which has been just handling machines, configuration on machines, hopefully to abstract that at least one layer more out. So real quick, who am I? You'll notice a difference between Roman's who am I and mine. He didn't have root, and I do. So I'm a recovering sysadmin. Some would say a recovering bastard operator from hell as well. I'm currently working on Apache CloudStack. Citrix pays me full-time to work on CloudStack. And so I'm a committer there. And CloudStack's a project that's incubating at the Apache Software Foundation. I'm also involved in a couple of other open source projects, including Fedora. And I'm missing FudCon to come talk about Puppet. I'll hit the last tail end of FudCon. I'm going to leave tonight to go catch that. But that's the other big open source project I'm involved in. How many of you have heard of, how many of you have not heard of the Phoenix project? Okay, so if you have a laptop or tablet open in front of you, you should Google the Phoenix project. It is an awesome book. I read it the day it came out, which was Tuesday, I think. It kept me up all night because I couldn't put it down. If you want a business book that explains the wonders of DevOps, that is it. And I highly encourage you to go check that out. Gene Kim and his collaborators have done an incredible job, and both from a DevOps perspective and a business perspective, it very artfully explains the business justification. The one thing that I didn't put up here on the slides is that I am a producer of very ugly slides. If you see colors other than black or white, that is special, and it is beautiful in my eyes, and it is not for anyone else. So essentially we've got about an hour and 10 minutes, hour and 15 minutes. I'm going to run down real quickly some of the tenets of CloudStack, discuss how it works, and then I'm going to jump into how you automate all of that infrastructure with Puppet, and then how to abstract that a layer above so that not just handling configuration, but actual deployment and provisioning. Not that we're necessarily trying to make Puppet a provisioning tool, but a virtualized environment is not really different than configuration. So, what's CloudStack? I used to do like 3 slides for this. I'm going to try and not do that here because, quite honestly, it's not very interesting. It's an open source infrastructure as a service cloud platform. It is currently Apache licensed. It started life GPL licensed, and after seeking out lots of contributors and making that change, we did essentially a similar change to what Puppet did, moving from GPL v2 to ASL. The really short, brief history is CloudStack began development in 2008. They had production deployments in 2009. They were really still kind of operating in stealth mode, though, in 2009 when they kind of announced themselves. They open sourced the project in 2010, and then in 2012 they moved to the Apache Software Foundation and started making inroads there. So here are the design goals that the original architects essentially drafted for CloudStack. And it's really that CloudStack is an orchestration platform. So CloudStack doesn't inherently do things that are incredibly interesting. It just automates them and allows you to apply logic to them as opposed to doing them manually or having a gazillion different tools to do those things. In many ways, it is to hardware, and as we're seeing more and more software, what Puppet is to configurations. Inherently, Puppet is not a sexy tool, but it makes life a lot better, and hopefully it makes your life a lot more enjoyable. So we're trying to interact with and integrate and control and orchestrate tons of different hardware. We're trying to do that via an API because no one wants to go do that manually. We've got to essentially assume that those are multi-tenant, that the environment is hostile, and so in doing that, you've got to provide that separation. You've got to be able to scale that out because no one wants to do it at 5 or 6 machines, but not be able to do it at 5 or 6,000. And then you have to design for failure. So it says best data paths. What that really means is life's going to suck at some point for everyone, and you need to have some redundancy there or ways to tolerate failure because there are too many moving pieces to ensure everything stays up all the time. The last one, clearly I have nothing to do with, which is a beautiful and functional UI. I make nothing that's beautiful. I have zero aesthetic capabilities, but there are some other folks who do. So just to take you really quickly on a real whirlwind tour here, I'm going to show you how we handle all of these resources. And so let's start with the physical servers, the hosts themselves. Typically what we're doing is we're managing hypervisors. Not necessarily the only thing that we're managing. We may manage bare metal and manage that via IPMI, but we're going to treat it as if it was a virtual machine. There's very little difference in how you would actually interact. These are the hypervisors we support today. There's 2 others in the wings, maybe 3 others. But KVM, Zen Server, Zen Cloud Platform, and VMware work today out of the box. And so that gets us to the physical hosts. We aggregate those physical hosts into clusters. That's typically, depending upon the hypervisor, 1 to 15 hosts. If you're doing bare metal, you can go a bit larger than that. But really, we're assuming that that's going to be 1 to 15 servers in a cluster. Cluster is where we enforce that things be the same. So essentially, we want the network to be the same on all the hosts within a cluster. We want the hypervisor to be the same. We want the CPU type to be the same within that cluster. That allows us to migrate workloads between hosts in the cluster, but it's also not such a large scope that it becomes restricted. So it's not like you have to go out and buy 5,000 machines that are all exactly the same, that are all configured the same, and that all have the same network access. So within the cluster, they are sharing storage. If you used shared storage, they will be sharing that storage to run VMs. That also limits your storage domain so that hopefully you're not punishing a single storage resource by hooking up n number of hosts where n is a very large 3 or 4 digit number. It's also the fault domain for individual VM availability. So if a VM falls over, we have the ability to restart it and restart it on another cluster, and it would preserve that. It would preserve essentially that disk image and just restart it on another machine. Let me step back. There are people who call that high availability. I think that's really fast mean time to recovery, or maybe even relatively fast mean time to recovery. I suppose it's a useful tool. I think it's a misnomer to call it high availability. A cluster is also that lowest level where we're making allocation decisions. So I'm not deciding when I go to decide where we're going to deploy a virtual machine. I'm not making that decision based upon what host name I like. I'm not looking for Odin or Thor or something like that. I'm looking for, hey, give me cluster 33 because there is enough capacity within the cluster. And so when we're going through the allocation algorithms, the allocation decisions are made at the cluster level, and then it will, once that decision is made, it'll figure out which host within the cluster to deploy to, but that's not actually an allocation decision per se. So the next level that we have up, and this is where things become a bit arbitrary. Typically, it's a pod. A pod's generally a rack or a row of racks, but that's completely arbitrary. Really, the assumption is that there's either a top of rack or an end of row switch. So there's going to be some relatively fast interconnects. The networking's all going to be, they're going to have access to the same guest network, but it's an arbitrary division. So I said when we were talking about clusters that we required that hypervisors be the same at the cluster level. That's the end of that enforcement, though. So you can have multiple hypervisors in a pod. So you can have your VMware, your KVM, your Xen server, and your bare metal all in 4 different clusters, but all residing in the same pod. And that's essentially not exposed to anyone. So the end user, and perhaps the unwritten statement here is that the end user is the one benefiting from all of this infrastructure. They're not going to be able to see the pods or clusters. They do, however, see the zones, and these are currently most analogous to an availability zone within EC2. So typically that's going to be a data center. Really the segment is that this is a single networking model, and so sometimes you will have multiple zones in a single data center. But typically you think of that as a geographic location, and this is something that the end user can see. It's the highest level of hardware, and it's the only thing that's exposed to the end user. So they can essentially decide where their machines are going to run, whether it's going to be the San Jose data center or the Chicago data center. That's the only thing that's exposed to them and is a real choice. So CloudStack doesn't really do storage in that it doesn't provide storage. So there's no CloudStack object storage. There's no CloudStack distributed storage, even though we can consume all of those. We've focused solely on the compute layer. So we're focused on orchestrating and consuming storage. There's really, I break it down into 3 types. There's local storage, and this is the storage that's on the hypervisors or the bare metal servers themselves. We will consume that. It's got some problems, so if the machine goes down, you just lost the storage for all of those VMs that were running there. It's typically faster than a shared storage resource that you would get with iSCSI or even fiber channel over Ethernet or NFS or anything else that's going to have to go over your network. The problem there is obviously bandwidth, and you're sharing it among other things. This gives you the ability to kind of shard that out if you need lots of storage, and you can split that up among a number of physical hosts. The largest clouds out there, when you start scaling to thousands of physical nodes, they are using this simply because trying to scale a very large SAN or NAS to do this is either very expensive or it is technically challenging, and it's easier to essentially architect your way out of that by tolerating failure in your application design than it is to try and toss gazillions of dollars at EMC or NetApp to provide you something scalable at the scale, at a massive scale. So then we have primary storage, which we make the assumption that it's shared. This is shared at the cluster level. This is where the running disk images live if they're not living on local storage. The only assumptions that we make are that all of the hosts within the cluster can write to that shared storage. So you need either a clustered file system, or you need it to be a block device, so something like iSCSI or RBD. But really anything that the hypervisors can all mount and write to. So clustered LVM, RBD, iSCSI, GFS2, things of that nature will take care of. Allowing all the hypervisors to write. So we restrict this to the cluster level simply because even when you get to 15 disks, you're starting, if you're running somewhere between 20 and 50 virtual machines per host, that's a lot of disk I/O that you're consuming. By keeping this at the cluster level, that minimizes the I/O load that you're going to experience and hopefully preserves some performance. At the same time, hopefully it's a little more robust than the hosts themselves, and you don't have nearly the concern about the host dying. So hopefully it's a little more robust as far as survivability. That is definitely an assumption, though, not necessarily true. So finally, we have secondary storage. So while primary storage is focused on running VMs, secondary storage is focused on immutable items that tend to be large. They tend to sit around for long periods of time and be read, although occasionally, of course, you're going to be writing those items up, but it's write once, read many times, and maybe occasionally destroy. So secondary storage stores snapshots of VMs, disk images, and ISOs. And rather than being at the cluster level, this is done at the entire zone level. So essentially, a minimum of one of these secondary storage resources per data center. Historically, that's always been NFS, partially because NFS is the lowest common denominator. You can get a hypervisor to talk to NFS because, again, it's the lowest common denominator, so all the hypervisors support it, with the exception of one, which is Hyper-V. But Hyper-V isn't currently supported, so we didn't really care in the early days. But now that we're starting to see other hypervisors being demanded, that may change. So one of the steps that we took a while back is to allow you to use object storage. So you can use either a Swift API or S3 API compatible object store and store these as essentially objects and call them over one of those two REST APIs. So now that we're kind of out of that physical layer for a moment, we have this concept of worker VMs, and I've termed them Borg VMs. We have a couple of different functions, and we'll talk about two right now, and there's a third that we'll get to in a minute. So just like individual Borg drones, these worker VMs have essentially no real mind of their own. They are being controlled by the hive. They are working towards a common goal, and essentially they replicate themselves to deal with the load at hand. So the first one is the console proxy VM. So a hypervisor and even your physical hardware can provide access to a console, whether that's a serial console or the actual VGA console on the back of the box. That's great. people at some point will need access to that, but that means that they have to authenticate to the hypervisor. And in a multi-tenant shared environment, that's a bad thing. So essentially, using the console proxy VM, it does exactly that. It proxies console access. And rather than making you VNC, have a VNC client or an RDP client, you're essentially using CloudStack provides a VNC client that is accessible via JavaScript. And so there's an AJAX VNC console that you can access via your web browser. You interact with it via your web browser, so you don't need Flash or any of those awful things that that people who try to provide you access to consoles generally require. CloudStack then gets to deal with authentication and authorization to allow you access to that console. So it looks, hey, do you actually have credentials to log into CloudStack? And if you do, does the machine that you're trying to access, is that yours, or have you been granted access to it? So we're abstracting away that hypervisor access and kind of putting a front end that hopefully is a lot safer in the process. Now, this isn't a replacement for Secure Shell or RDP, but it's certainly no more painful than DRAC or Loam or ILO. So the same things that you would use in a physical realm for DRAC would be what you would do here. Essentially, you don't have network connectivity or the box has completely fallen over. The good thing about the console proxy VM is that it's stateless, so we don't care if the box goes down. We'll start another one. If it starts to get overloaded, we'll spin up more to handle the load. There's no state. You can scale up until you start running out of actual compute capacity. The next one is a secondary storage VM. So while we have secondary storage as a resource, we have the SSVM to do things with that resource. So some of the things we have are copying snapshots. When a virtual machine image is snapshotted, that snapshot still resides on primary storage. And the assumption is that hopefully high-performing primary storage is expensive for you to consume with things like a snapshot. So we essentially allow you to copy that off, and the secondary storage VM, again, abstracts away the need for people to have hypervisor access or storage access, and it will go acquire that snapshot. It'll put it back to secondary storage, which hopefully is a cheaper, more commodity storage for you. Likewise, because it's storing the original disk images, it will ferry those between back to primary storage so that when you deploy a virtual machine, it can be turned on. That essentially, that two-way street is where a lot of the activity that the SSVM handles. But no one wants this single palace where you can't get anything out. So the secondary storage VM is also the public-facing storage outlet. And so if you want to push up an ISO or a disk image, you use the web front end of the secondary storage VM to do so. You also can download your snapshots or your disk images from there as well. And finally, the last thing is when you have snapshots that are sitting around in storage, you don't want to keep them ad infinitum. You want to have some policy, so I will keep no more than 10 snapshots of any given virtual machine, which means you need to be scavenging those, and no one wants to do that manually. So the secondary storage VM ensures that you have enough snapshots in the chain that you can get back to a disk, and also that you're not keeping around more than your policy requires. Have I confused anyone yet? Does anyone have questions? Feel free to interrupt me. I'm happy to drone on, and I know that this is post-lunch and people are close to coma, but feel free to yell or scream to get my attention. So networking is the bane of most cloud administrators' existence. tends to get really complex really quick. It's anyone in here a network admin? One person who won't raise his hand in the back. Generally speaking, network admins are still back in the 70s and 80s from a technology perspective. If you go and start taking training on Cisco products, they're telling you to do things like SSH, if they're really modern, SSH into your router or your switch and do configurations in the terminal. Life has moved on considerably since then. We're starting to see people that are not the traditional network vendors do a lot of innovation. And so this idea of things like configuration management, it's shocking to most network guys. I'm going to assume because you're here that you're not one of those. So we'll start with that. There's also control issues. So most network guys can't conceive of end users getting to do things like changing firewall configuration, dropping load balancers into place, or getting access to a VLAN. So we'll start with VLANs, because VLANs are what people know. They've been around for a while. People are comfortable with them. This is traditional layer 2 isolation. And in this, CloudStack essentially gets a block of VLANs. And you say VLANs 1200 to 1400 are for CloudStack, and you deal with allocating them. And so CloudStack will allocate those at least one per user. When a user deploys their first virtual machine, they will get allocated a VLAN. That is theirs and only theirs, and they get at least one. They can acquire more if you permit them. You can set a limit on how many they can acquire. So anyone know the limit of VLANs in a single network? Yeah, about 4K. So you start running into this really quickly when you can have users who can request 3, 4, 5, 20 VLANs at a time. There's a bigger problem, though, that I think people tend to run into quicker, and that's that their hardware won't keep up with 4,000 VLANs at the full network speed. So typically, most of what you would see in an enterprise grade, i.e. not an ISP grade network gear, is that it'll handle about 1,000 VLANs, which is a much smaller number. And the gear that will get you up to 4K is orders of magnitude more expensive than the stuff that'll get you to 1,000. So those are some of the inherent limitations. And if you're trying to scale this to any real size, VLANs just aren't going to work. So what comes after VLANs? And the group that answered this best was really Amazon. They had this idea of, they call it security groups, essentially using layer 3 isolation. And so what you're really doing, instead of having a single router that provides isolation, or an ASA or some similar firewall that has ACLs that it's maintaining in a centralized location, or maybe even redundantly using HSRP across two, you're pushing that down to the hypervisor level. And that gives you a lot more scalability, but it also increases complexity, because now instead of managing a single ASA or two ASAs operating in tandem, you have n number of choke points, which is okay, because it just so happens we have a infrastructure as a service platform to orchestrate things like that. So this is far more scalable, potentially decentralized. You're potentially going to have these workers, I just again call them Borg, who are going to do nothing but make sure that those ACLs are in sync. Who's familiar with EB tables in Linux? A few people. So this is really using, in most cases, EB tables. You're going to get to see some of my beautiful artwork. This is as beautiful as I can generate, and I apologize. But essentially, we're going to make the assumption that that layer 2 network is somewhat trusted. We're going to assume that you can control what plugs into it and what does not, and that you're only going to plug in hypervisors into that physical port. And then you have the actual physical device itself, the physical interface. We're going to assume that essentially that that's only going to be hypervisors that are connected to it, and the hypervisor itself is not going to directly, logically talk to that physical interface. It's going to create a bridge device, and that bridge is going to allow all the virtual machines to connect to the network, but that also makes the bridge the natural point at which to begin filtering. So in this example, where we have a single machine, single hypervisor with 3 VMs running on it, if the virtual machines want to talk to the outside world, or if the outside world wants to talk to the virtual machines, or if the virtual machines want to talk to each other, they have to connect through that bridge device. And the bridge device, except for egress, ingress is always denied by default. So unless you have explicitly permitted traffic, it will not pass. And essentially, that limits the amount of traffic. That means that you've also got a pretty flat layer 2 network, which tends to scare people, except when you realize that it's denied by default, so you don't have things like broadcast storms migrating off of the, at least from the VMs, out onto that layer 2 network. So you can have a pretty large flat layer 2 network. And we're typically seeing the upper bounds of this right now at about 30,000 physical hosts. And they're maintaining 5,000 or 6,000 hosts per network, per flat layer 2 network, and still able to keep that under control. It's straight IP filtering. So as if you were doing IP tables, EB tables is the bridged version of that. So essentially, anytime any traffic comes into that into the bridge device, it's got to match yes. So, and you can see what happens when you have 2 of those. Even if your VM on one machine wants to talk to a VM on another machine, it's got to pass through that through bridge devices twice. And so essentially, by default, CloudStack will check every few minutes to ensure that the bridge device still has the current configuration, unless there is an active change, and then it will try and go out and push the change proactively. But it's continuously checking state, much like you would expect from Puppet Labs firewall. Anyone confused by security groups? Yes. There's a question, and we're waiting for a microphone.
So I'm curious to know where the ACL is exactly applied. Is it applied at the virtual machines VNIC that connects to the bridge device, or is it applied to the hypervisor's Ethernet interface that connects to the switch?
Neither. It's applied to, it's not applied to either of those 2 physical interfaces. It's applied to the actual logical bridge device. And so it's not applied to like /dev/eth0. It's applied to /dev bridge 0. And essentially that's because if you were doing it with the devices themselves, you would really be doing that with IP tables. And we're doing this with EB tables, so one set of rules for the entire set of VMs that are on that machine. And we're actually doing some things to enhance that. So rather than using straight, we're using IP set to make that a lot more scalable, because we found that once you hit about 5,000 or 6,000 sets of rules, that things start to bog down really quickly. And you can get at least another order of magnitude out of that using IP set. All right, so I don't think that that we're in any danger of really exhausting the ability of security groups. Amazon's still using security groups, and they by far are the 800-pound gorilla. If they're not having problems, unless you happen to work for Google, you're probably not going to run into problems either. But that's a scalability question. That's not necessarily a flexibility question. So kind of the next generation thing that's come along is software-defined networks. And the first experimentation that CloudStack had with this was just turning on Open vSwitch on the hypervisors and then managing GRE overlay tunnels within Open vSwitch. So in many ways, CloudStack became, I don't want to say the flow controller, but it orchestrated the individual Open vSwitch units on each of the hypervisors, set up GRE overlay tunnels between virtual machines on those hypervisors, and if you needed that level of flexibility, you could certainly get it out of OVS. The next step up was a real flow controller from the folks at Nicira. Nicira NVP came along, and CloudStack can essentially orchestrate the flow controller in Nicira to deal with all of the traffic from the hypervisors. And then there's a couple of more SDN efforts that are currently going on, and some of them are actually ready to go, but not in a release, and others should be very soon. So Big Switch and MidoNet will be coming shortly. And we have a question for which there's a...
I'm battery challenged on the
Could you comment from the user of this infrastructure as a service what type of network capabilities they would have? So I understand the simplest case, you have security zones with VLANs, and you can put your nodes in the different VLANs, and then you get firewall rules or rules between the different zones. With the SDN technology, what are some of the common, more flexible network things the end users could do?
All right, so the question is essentially what kind of capabilities does SDN give you in an infrastructure as a service environment that you would not have with things like your traditional VLANs? It's very intense isolation is one of them. So for instance, with OVS, it's machine-to-machine tunnels, which you can then do things like encryption over for a lot greater sense of security. There's folks who are doing data center connects, which typically they would have done with something like MPLS. So you take your local data center, you hook it up to your cloud data center, quote unquote, and your machines can talk as if they were on the same LAN. But this is a lot easier and more scalable to pull off than MPLS. And quite honestly, it's some of the things that people are starting to demand just from the complexity of their architecture, where you couldn't have done it at the VLAN level simply because of scale. Especially folks who are very large into a lot of test dev environments, and they want to sequester each one of those. Doing that with VLANs is relatively expensive compared to doing it with something like a GRE tunnel or STT.
So
Yes.
Can you comment on the different open sources for the SDN? So are you saying that Big Switch, Nicira, I believe Big Switch uses Headlight, I forgot the open source. So what open sources of SDN part of CloudStack today?
So Open vSwitch is an SDN technology, although it's not an inherent flow controller. It's not OpenFlow itself. That is available in CloudStack today. Nicira is not open source. That's actually, I think they actually want to sell you physical hardware. It will run on regular hardware, but that is a proprietary product but it's taking advantage of things like OpenFlow and Open vSwitch. Big Switch has two different offerings. They have, I think it's Flashlight, which is their open source flow controller. They've got another flow controller that is not open source, although both of those should work in the next release of CloudStack, which should be here in March. Metacura, I think, is still, I don't think that is open source at present. So, yeah.
All of them or some of them, or maybe only Big Switch is part of it? Or
CloudStack currently has support for OVS and Nicira, and in what is actually in a release so far. CloudStack will have support for Big Switch and MitoNet in an upcoming release.
okay, thanks.
All right, so we talked a little bit about these, the other Borg drone that we have. And so essentially we think that cloud computing is all about commodity. And the lowest level of commodity that we think you can get to currently is a virtual machine. So out of the box, CloudStack provides you with what is a virtual router, or we call it a virtual router. It does a number of networking services. So it'll provide you with DHCP, VLAN allocation, firewalling, NAT, port forwarding, routing, a VPN endpoint, as well as a load balancer, all of which gets orchestrated by CloudStack. If you're using VLANs, each account gets their own virtual router, which they cannot directly interact with, but it's dedicated to them, both for performance and security reasons. And this allows them to, an end user to very cheaply configure things like a load balancer that you would have normally had to drop an F5 or something of that nature into place, or you would have had to have set up a virtual machine to run something like HA proxy or traffic server. And this allows you to do it all within the same framework. It's a native part of CloudStack, so you need one, just spin one up. You want to maintain it redundantly, that's no problem either. We can do virtual router redundancy protocol to ensure that there is one available at all times. So certainly a possibility to really commoditize all of these networking functions into something that's easily consumable and doesn't require any real capital layout. So clearly we weren't the only people who thought of this. There's a lot of virtual networking hardware out there now, and I say virtual and hardware, realizing that they are contradictory. So there's the Cisco Nexus 1000V, and they've got a new ASA product that's virtualized as well that's coming out. The NetScaler VPX and the F5 Big IP also has a virtual appliance. You can deploy those and control those in the same way, and presumably anything else that you could get in a virtual networking form. So there's some folks who are working on things like Viata right now, and maybe we'll see that at some point. But a lot of people have tons of money invested in their physical networking hardware, and they don't want to get rid of that. So CloudStack will talk to a number of physical networking pieces. You'll notice Cisco isn't in here, and that's because historically they have not had an API to talk to. That is starting to change, but it's not there, and I need to drastically hurry up. So we also have a management server that actually does all of the business of orchestrating this. The management server is stateless. You can spin n number of them up or have none of them running if you don't mind staying frozen. But essentially they are horizontally scalable, and they will deal with orchestrating all of those resources that we've been talking about, and also providing isolation between what others are orchestrating. State is stored in a database, so the management server itself is not is not a source of state. And of course, there's that beautiful UI that everybody talks about that I have nothing to do with. This is the end user API, which is really quite flashy, all things considered. CloudStack has a couple of APIs. The first is the native API, and you can check the native API out at that link. That native API is a very REST-like API, and folks seem to enjoy working with that. We'll talk about it a little bit later when we talk about orchestrating that with Puppet. We also have an EC2 and S3 translation layer. So we'll take EC2 and S3 API calls inbound, translate them to the CloudStack API, and just keep on acting as if we were EC2 or S3. So you can use things like Bodo to deploy. If that's already part of your tooling, you can talk to that AWS layer. If you want more information, you should check out one of these 3 resources. The mailing list is not, this particular mailing list isn't too high volume, and you can get help easy. IRC's a lot more interactive, and there's lots of folks who are running this at incredible scale that hang out in IRC. And just as you would go get help for Puppet in IRC, you would expect the same kind of thing in Hash CloudStack. All right, so that kind of lays the foundation for what we're really here to talk about. So I've got 2 things I want to talk about how you would use Puppet to really take automation to the next level in your cloud environment. And so this first section I did not write. I'm taking advantage of Jason Hancock's awesome work, and I'm standing on his shoulders to show off this. So it's great that you can have this cloud platform. You can deploy 500 VMs in 10 minutes, but you need a way of dealing with that. So, we kind of have things like we could go with the ENC route. We could have host names that are that we could regex off of. A number of ways that we can deal with being able to classify and apply configuration to those machines. But starting with a couple of assumptions is that we want to have the minimum number of disk images around. When someone comes to deploy something, we do not want to have 50 copies of CentOS 6.3. We want to have 1 copy of CentOS 6.3 and deal with package deployment and configuration with a tool that was built for that, not with throwing more storage at it. We also don't want any manual intervention. So I don't want to have to shell into a machine, and I want all of the configuration driven by Puppet. So really this means I want to make 1 API call that launches a virtual machine, then gets out of the way and watch the automation just do wonderful things. So you can use auto signing, and as a matter of fact, one of the unwritten things in this presentation is that I assume that you will. That's not necessarily a good thing. There are security issues, which I'm sure you're aware of if you're using auto signing. If you take a look at Jason's blog, he'll tell you ways of getting around this, but there are some active bugs in how Puppet responds to that. So you also want, we're making the assumption that you want to get a machine usable really quick. So turn off splay, which is that delay between the service starting up and it reaching out to the Puppet master. And you're also probably not going to get away with running Puppet as cron unless you're okay with a delay. If you want Puppet running as soon as the machine is up and has network access, you're going to have to use the daemon and not just call Puppet via cron. So again, we have this way of, a number of ways of classifying nodes. We have a dashboard, which is not a very scalable way of doing it, although it's very pretty. We have hostname-based regex. We can manually enter in names into site or node.pp. We can have a ENC. And there's a gazillion other ways we can do this, but we're going to talk about using facts to do it. Essentially, we're querying for things about the machine that distinguish it, and one of the things that we want to use is user data. So just like in EC2, we can specify user data about a VM deployment, and when we're supplying that, the VM itself can read that user data, and so it's pretty trivial to make that into a fact. And so here's something that we would probably put into one of those user data sections: a role, maybe location, maybe environment, potentially a host of other things. So I put a link here. This is to the custom fact stuff that Jason actually wrote. And that will essentially create a fact on every machine that you deploy that provides you with that user data as a fact. So then how do we take that and do something interesting with it? So you treat everyone, or at least the things that are in your CloudStack environment, as a default node. And that means that you don't have to add nodes to site.pp or use an ENC. You can just use role. And so here's a very skeletonized site.pp, which says that the default node includes base. And so let's look at base.pp. I think we're missing at least one line at the bottom to close that last bracket. But essentially, it's you've got a case statement here, and if role matches some role, then it includes some module. If it matches other role, it includes some other module. And so this is a really simple skeletonized way of doing this, and you would probably include multiple modules in the process, but that's about as simple. And I'm starting to run out of time, and I knew I was going to do this, so you definitely owe it to yourself to check out Jason's blog. He did wonderfully awesome things in his original environment that he did this in, including purging his terminated instances, because you do things other than just turn instances up. When they need to go away, they disappear, and you don't want to get alerted by Nagios or whatever your monitoring system is. Dealing with environments. To tell you some of the success that Jason had, he was saving 6 figures a year in the single process that he automated in this fashion, and he was able to turn up Unreal Tournament and Doom environments on their lunch hour without anyone realizing it, because he could very dynamically scale up instances, and I think those manifests are still in that particular company's Puppet repo. But so this is hopefully just to whet your appetite for some of the things you can do with automating the VM configuration. Let's talk about the next level. This is done by Dan, largely. I beat Dan up for about 6 months to do this work because they had done it for another platform. And then he did it for a third platform, and I got really jealous. And then I think he cowed to my incessant begging. So essentially, what we do today is we say, okay, go deploy a machine, and we have some tools to do that, like we have Cobbler that will go out and deploy physical machines. We have Box Grinder that will deploy cloud or virtualized images of machines. But you've still got this other resource that's managing your deployment of instances. And really, you want to be able to define your infrastructure as code. And so essentially the work that Dan did was to define CloudStack resources within Puppet. So CloudStack has an API, that deploy virtual machine API, right? So you can deploy a virtual machine with a single API call. Puppet, on the other hand, typically converts those freshly provisioned VMs into something that's actually useful. So much like Reese's combining chocolate and peanut butter, if you could combine those two to be able to say, start from nothing but having the capacity, deploy the virtual machines in from code, and then configure them with config management that Puppet typically does, you end up with Reese's Peanut Butter Cups. But so you can check out the resource that Dan wrote here on GitHub. I will say that it's probably still a bit raw, although we know of at least one place using it in production. If you find problems, I'm sure he would love to see pull requests. So let's walk through some of how this works. So let's start by defining some infrastructure, right? So we're going to define a web stack here. We're going to have a web server, and we're going to have a database server. They're going to be two different machines, and we're saying that there's going to be an instance, Web1, and another instance, DB1, and you'll see that we've set their role with that group. Now that's doing two things. That's telling the group in the API call that CloudStack is going to make for deploy virtual machine that is the data that should be in the group field. Now this is different than user data, and that's essentially turning the model that we just talked about that Jason had, and turning that so that CloudStack is actually serving as somewhat of an ENC. We're saying ensure present, so we want the instance to be there when we actually provision it. And then, so we also probably want to set some defaults. So these are also things that we could be defining. So we could define the network, we could define the data center, the size of the instance, and a number of other things. And so then when we say that we want to deploy Web1, all of those are part of that default.
Hey, Dave.
Yes.
I think we're subject to building it on a Mac and running it on a PC, some of our formatting. Is this, because I can see you're losing some data, right?
I am down at the bottom.
Is that important to you?
Okay.
Okay.
Not materially.
Okay.
But the problem is probably me going from OpenOffice on Linux to, I assume, Windows in there.
It is.
Yeah. So this allows you to set defaults that you're going to assume, which means that you can get away with 3-line instance definitions. So now the Puppet machines and their configuration are deployable all from Puppet. This allows you to do that with Google Compute Engine and OpenNebula, because something similar exists for both of those as well. This means that when Puppet runs, it's going to go and say, I have a machine that I need to deploy, or I need to check the state of the machine to make sure that it is deployed. And essentially your entire, what would have been VMs that you would have deployed manually or hardware that you would have racked manually is now defined in code, which is yet another layer of abstraction for your infrastructure. What else can I tell you? Because I've got about 8 minutes left for questions. No one has any questions. Anyone doing something similar to this with EC2 or GCE now? You are? What are you doing with it? Oh, you're doing it with CloudStack? So do you have, my mail server is this configuration so that if it all went away, you could redeploy it? That is the thing that personally I like is I can say, here's the definition of a Hadoop cluster. I need to redeploy a Hadoop cluster. I can say, go deploy that entire stack again for me.
So the dumb question for the day is, do you have templates ready-made for different kinds of personalities like you were talking about before with the Borg? Do you have templates for those predefined so that we can drop in to Puppet, or is it up to us to kind of piece those together?
So for predefined templates, there are people who make predefined templates. I personally despise golden images. And you'll see, I tend to like Cobbler, I tend to like Box Grinder, things that are going to build an image on the fly, even if that image is a steady state definition. And so I also said that I didn't want, one of the goals that I stated, and it's one of the goals from Jason as well, is we didn't want a MySQL template and a Postgres template and an Apache template and an Nginx template. We want a CentOS 6.3 x86 64 template. And maybe we'll also have an Ubuntu 12.04 template, but we don't want to have sprawled just in images, because that's much harder and more difficult to maintain. So do those exist? Yes. So the Borg, for instance, that we talked about, that's a single Debian image today. So, and that can morph itself into any of those three roles. So it can become that virtual router. It can become a secondary storage VM or a console proxy VM. We have a few pre-built templates for things like Ubuntu and CentOS, and then there are people who are making them by the dozens, or you can go to SUSE Studio, or there's a Box Grinder service on Amazon that'll spew out disk images that you can then import. Anyone else have questions?
So I'm going to ask a very fundamental question. So today, if I want to just, I have a bunch of servers, and then if I want to deploy CloudStack, can I use, I'm looking at these links you gave me, can I use one of these tools to automatically configure using single template, like the way you said, CentOS template, for instance, get the CloudStack deployed on multiple servers simultaneously? Is that possible?
So there is a Puppet CloudStack module. It has not kept up with the latest version. It's out there. If you go look on my GitHub account, which is github.com/ke4qqq.
Oh, that's too fast.
Yeah. Hey, Don, can you go back to slide 1? So my Twitter handle, that's what, if you put that into GitHub, there is a CloudStack Puppet module there. It's in rough shape for the latest version and needs some maintenance, but it is there, and that will get you set up and installed. It won't handle configuration yet, because there are a gazillion different options, like what network do you want, etc. And while I've commented out all of those things that would define that, so you could uncomment them and go from there if you really wanted to.